a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Lockheed SR-71 Blackbird. The Lockheed Senior 71 Blackbird is a long-range Mach 3 strategic reconnaissance aircraft that was operated by the United States Air Force. It was developed as a black project from the Lockheed A-12 reconnaissance aircraft in the 1960s by Lockheed and its Skunk Works division. American aerospace engineer Clarence Kelly Johnson was responsible for many of the design's innovative concepts. During aerial reconnaissance missions, the Senior 71 operated at high speeds and altitudes to allow it to outrace threats. If a surface-to-air missile launch were detected, the standard evasive action was simply to accelerate and outfly the missile. The Senior 71 was one of the first aircraft to be designed with a reduced radar cross-section. The Senior 71 served with the U.S. Air Force from 1964 to 1998. A total of 32 aircraft were built. 12 were lost in accidents, but none were lost to enemy action. The Senior 71 has been given several nicknames, including Blackbird and Habu. Since 1976, it has held the world record for the fastest air-breathing manned aircraft, a record previously held by the related Lockheed A-12. Background: Lockheed's previous reconnaissance aircraft was the relatively slow U-2, designed for the Central Intelligence Agency. In late 1957, the CIA approached the defense contractor Lockheed to build an undetectable spy plane. The project, named Archangel, was led by Kelly Johnson, head of Lockheed's Skunk Works unit in Burbank, California. The work on Project Archangel began in the second quarter of 1958, with aim of flying higher and faster than the U-2. Of 11 successive designs drafted in a span of 10 months, A-10 was the frontrunner. Despite this, however, its shape made it vulnerable to radar detection. After a meeting with the CIA in March 1959, the design was modified to have a 90% reduction in radar cross-section. The CIA approved a $96 million contract for Skunk Works to build a dozen spy planes, named A-12, on the 11th of February 1960. The 1960 downing of Francis Gary Powers's U-2 underscored its vulnerability and the need for faster reconnaissance aircraft such as the A-12. The A-12 first flew at Groom Lake, Nevada, on the 25th of April 1962. 13 were built. 2 variants were also developed, including 3 of the A-12 Interceptor prototype, and 2 of the M-21 drone carrier. The aircraft was meant to be powered by the Pratt & Whitney J-58 engine, but development ran over schedule, and it was equipped instead with the less powerful Pratt & Whitney J-75 initially. The J-58s were retrofitted as they became available, and became the standard power plant for all subsequent aircraft in the series, as well as the Senior 71. The A-12 flew missions over Vietnam and North Korea before its retirement in 1968. The program's cancellation was announced on the 28th of December 1966, due both to budget concerns and, because of the forthcoming Senior 71, a derivative of the A-12. Senior 71. The Senior 71 designation is a continuation of the pre-1962 bomber series. The last aircraft built using the series was the XB-70 Valkyrie. However, a bomber variant of the Blackbird was briefly given the B-71 designator, which was retained when the type was changed to Senior 71. During the later stages of its testing, the B-70 was proposed for a reconnaissance/strike role, with an RS-70 designation. When the A-12 performance potential clearly was found to be much greater, the Air Force ordered a variant of the A-12 in December 1962. Originally named A-12 by Lockheed, the Air Force version was longer and heavier than the A-12, with a longer fuselage to hold more fuel, 2 seats in the cockpit, and reshaped chines. Reconnaissance equipment included signals intelligence sensors, a side-looking airborne radar, and a photo camera. The CIA's A-12 was a better photo reconnaissance platform than the Air Force's A-12, since the A-12 flew somewhat higher and faster, and with only one pilot, it had room to carry a superior camera and more instruments. During the 1964 campaign, Republican presidential nominee Barry Goldwater repeatedly criticized President Lyndon B. Johnson and his administration for falling behind the Soviet Union in developing new weapons. Johnson decided to counter this criticism by revealing the existence of the A-12 Air Force interceptor, which also served as cover for the still-secret A-12 and the Air Force reconnaissance model since July 1964. Air Force Chief of Staff General Curtis LeMay preferred the senior designation and wanted the RS-71 to be named Senior 71. Before the July speech, LeMay lobbied to modify Johnson's speech to read Senior 71 instead of RS-71. The media transcript given to the press at the time still had the earlier RS-71 designation in places, creating the story that the president had misread the aircraft's designation. Johnson only referred to the A-11 to conceal the A-12, while revealing that there was a high-speed, high-altitude reconnaissance aircraft. In 1968, Secretary of Defense Robert McNamara cancelled the F-12 interceptor program. The specialized tooling used to manufacture both the A-12 and the Senior 71 was also ordered destroyed. Production of the Senior 71 totaled 32 aircraft, with 29 Senior 71As, 2 Senior 71Bs, and the single Senior 71C. Overview. The Senior 71 was designed for flight at over Mach 3 with a flight crew of 2 in tandem cockpits, with the pilot in the forward cockpit and the reconnaissance systems officer operating the surveillance systems and equipment from the rear cockpit, and directing navigation on the mission flight path. The Senior 71 was designed to minimize its radar cross-section, an early attempt at stealth design. Finished aircraft were painted a dark blue, almost black, to increase the emission of internal heat and to act as camouflage against the night sky. The dark color led to the aircraft's nickname, Blackbird. While the Senior 71 carried radar countermeasures to evade interception efforts, its greatest protection was its combination of high altitude and very high speed, which made it almost invulnerable. Along with its low radar cross-section, these qualities gave a very short time for an enemy surface-to-air missile site to acquire and track the aircraft on radar. By the time the SAM site could track the Senior 71, it was often too late to launch a SAM, and the Senior 71 would be out of range before the SAM could catch up to it. If the SAM site could track the Senior 71 and fire a SAM in time, the SAM would expend nearly all of the delta V of its boost and sustainer phases just reaching the Senior 71's altitude. At this point, out of thrust, it could do little more than follow its ballistic arc. Merely accelerating would typically be enough for an Senior 71 to evade a SAM. Changes by the pilots in the Senior 71's speed, altitude, and heading were also often enough to spoil any radar lock on the plane by SAM sites or enemy fighters. At sustained speeds of more than Mach 3.2, the plane was faster than the Soviet Union's fastest interceptor, the Mikoyan-Gurevich MiG-25, which also could not reach the Senior 71's altitude. During its service life, no Senior 71 was shot down. Airframe, canopy, and landing gear. On most aircraft, use of titanium was limited by the costs involved. It was generally used only in components exposed to the highest temperatures, such as exhaust fairings and the leading edges of wings. On the Senior 71, titanium was used for 85% of the structure, with much of the rest polymer composite materials. To control costs, Lockheed used a more easily worked titanium alloy which softened at a lower temperature. The challenges posed led Lockheed to develop new fabrication methods, which have since been used in the manufacture of other aircraft. Lockheed found that washing welded titanium requires distilled water, as the chlorine present in tap water is corrosive. Cadmium-plated tools could not be used, as they also caused corrosion. Metallurgical contamination was another problem. At one point, 80% of the delivered titanium for manufacture was rejected on these grounds. The high temperatures generated in flight required special design and operating techniques. Major portions of the skin of the inboard wings were corrugated, not smooth. Aerodynamicists initially opposed the concept, disparagingly referring to the aircraft as a Mach 3 variant of the 1920s-era Ford Trimotor, known for its corrugated aluminum skin. The heat would have caused a smooth skin to split or curl, whereas the corrugated skin could expand vertically and horizontally and had increased longitudinal strength. Fuselage panels were manufactured to fit only loosely with the aircraft on the ground. Proper alignment was achieved as the airframe heated up and expanded several inches. Because of this, and the lack of a fuel sealing system that could handle the airframe's expansion at extreme temperatures, the aircraft leaked JP-7 fuel on the ground prior to takeoff. The outer windscreen of the cockpit was made of quartz and was fused ultrasonically to the titanium frame. The temperature of the exterior of the windscreen reached during a mission. Cooling was carried out by cycling fuel behind the titanium surfaces in the chines. On landing, the canopy temperature was over 300 degrees Celsius. The red stripes featured on some Senior 71s were to prevent maintenance workers from damaging the skin. Near the center of the fuselage, the curved skin was thin and delicate, with no support from the structural ribs, which were spaced several feet apart. The Blackbird's tires, manufactured by B.F. Goodrich, contained aluminum and were filled with nitrogen. They cost $2,300 and would generally require replacing within 20 missions. The Blackbird landed at over 170 knots and deployed a drag parachute to stop. The chute also acted to reduce stress on the tires. Acquisition of titanium. Titanium was in short supply in the United States, so the Skunk Works team was forced to look elsewhere for the metal. Much of the needed material came from the Soviet Union. Colonel Rich Graham, Senior 71 pilot, described the acquisition process. The airplane is 92% titanium inside and out. Back when they were building the airplane, the United States didn't have the ore supplies and ore called rutile ore. It's a very sandy soil, and it's only found in very few parts of the world. The major supplier of the ore was the USSR. Working through third world countries and bogus operations, they were able to get the rutile ore shipped to the United States to build the Senior 71. Shape and threat avoidance. The first operational aircraft designed around a stealth aircraft shape and materials, the Senior 71 had several features designed to reduce its radar signature. The Senior 71 had a radar cross-section around, drawing on early studies in radar stealth technology, which indicated that a shape with flattened, tapering sides would reflect most energy away from a radar beam's place of origin. Engineers added chines and canted the vertical control surfaces inward. Special radar-absorbing materials were incorporated into sawtooth-shaped sections of the aircraft's skin. Cesium-based fuel additives were used to somewhat reduce exhaust plumes' visibility to radar, although exhaust streams remained quite apparent. Kelly Johnson later conceded that Soviet radar technology advanced faster than the stealth technology employed against it. The Senior 71 featured chines, a pair of sharp edges leading aft from either side of the nose along the fuselage. These were not a feature on the early A3 design. Frank Rogers, a doctor at the Scientific Engineering Institute, a CIA-front organization, discovered that a cross-section of a sphere had a greatly reduced radar reflection, and adapted a cylindrical-shaped fuselage by stretching out the sides of the fuselage. After the advisory panel provisionally selected Convair's fish design over the A3 on the basis of ARS, Lockheed adopted chines for its A4 through A6 designs. Aerodynamicists discovered that the chines generated powerful vortices and created additional lift, leading to unexpected aerodynamic performance improvements. The angle of incidence of the delta wings could be reduced for greater stability and less drag at high speeds, and more weight carried, such as fuel. Landing speeds were also reduced, as the chines vortices created turbulent flow over the wings at high angles of attack, making it harder to stall. The chines also acted like leading-edge extensions, which increased the agility of fighters such as the F-5, F-16, Fa-18, MiG-29, and Su-27. The addition of chines also allowed the removal of the planned canard foreplanes. Air inlets. The air inlets allowed the Senior 71 to cruise at over Mach 3.2, while keeping airflow into the engines at the initial subsonic speeds. Mach 3.2 was the design point for the aircraft, its most efficient speed. However, in practice the Senior 71 was sometimes more efficient at even faster speeds, depending on the outside air temperature, as measured by pounds of fuel burn per nautical mile traveled. During one mission, Senior 71 pilot Bryant Shaw flew faster than usual to avoid multiple interception attempts. Afterwards, it was discovered that this had reduced fuel consumption. At the front of each inlet, a pointed, movable cone called a spike was locked in its full forward position on the ground and during subsonic flight. When the aircraft accelerated past Mach 1.6, an internal jack screw moved the spike up to inwards, directed by an analog air inlet computer that took into account pitot-static system, pitch, roll, yaw, and angle of attack. Moving the spike tip drew the shock wave riding on it closer to the inlet cowling until it touched just slightly inside the cowling lip. This position reflected the spike shock wave repeatedly between the spike center body and the inlet inner cowl sides, and minimized airflow spillage, which is the cause of spillage drag. The air slowed supersonically with the final plane shock wave at entry to the subsonic diffuser. Downstream of this normal shock, the air is subsonic. It decelerates further in the divergent duct to give the required speed at entry to the compressor. Capture of the plane's shock wave within the inlet is called starting the inlet. Bleed tubes and bypass doors were designed into the inlet and engine nacelles to handle some of this pressure, and to position the final shock to allow the inlet to remain started. In the early years of operation, the analog computers would not always keep up with rapidly changing flight environmental inputs. If internal pressures became too great and the spike was incorrectly positioned, the shock wave would suddenly blow out the front of the inlet, called an inlet unstart. During unstarts, afterburner extinctions were common. The remaining engine's asymmetrical thrust would cause the aircraft to yaw violently to one side. SAS, autopilot, and manual control inputs would fight the yawing, but often the extreme off angle would reduce airflow in the opposite engine and stimulate sympathetic stalls. This generated a rapid counter-yawing, often coupled with loud, banging noises, and a rough ride during which crews' helmets would sometimes stripe their cockpit canopies. One response to a single unstart was unstarting both inlets to prevent yawing, then restarting them both. Lockheed later installed an electronic control to detect unstart conditions and perform this reset action without pilot intervention. Beginning in 1980, the analog inlet control system was replaced by a digital system, which reduced unstart instances. Engines. The Senior 71 was powered by two Pratt & Whitney J58 axial flow turbojet engines. The J58 was a considerable innovation of the era, capable of producing a static thrust of. The engine was most efficient around Mach 3.2, the Blackbird's typical cruising speed. At lower speeds, the turbojet provided most of the compression. At higher speeds, the engine largely ceased to provide thrust, the afterburner taking its place. Air was initially compressed by the inlet spike and subsequent converging duct between the center body and inlet cowl. The shock waves generated slowed the air to subsonic speeds relative to the engine. The air then entered the engine compressor. Some of this compressor flow was removed after the fourth compressor stage and went straight to the afterburner through 6 bypass tubes. Air passing through the turbojet was compressed further by the remaining 5 compressor stages, and then fuel was added in the combustion chamber. After passing through the turbine, the exhaust, together with the compressor bleed air, entered the afterburner. At around Mach 3, the temperature rise from the intake compression, added to the engine compressor temperature rise, reduced the allowable fuel flow, because the turbine temperature limit did not change. The rotating machinery produced less power, but still enough to run at 100% RPM, thus keeping the airflow through the intake constant. The rotating machinery had become a drag item, and the engine thrust at high speeds came from the afterburner temperature rise. Maximum flight speed was limited by the temperature of the air entering the engine compressor, which was not certified for temperatures above. Originally, the Blackbird's J58 engines were started with the assistance of two Buick Wildcat V8 internal combustion engines, externally mounted on a vehicle referred to as an AG330 start cart. The start cart was positioned underneath the J-58 and the two Buick engines powered a single, vertical drive shaft connecting to the J-58 engine and spinning it to above 3,200 rpm, at which point the turbojet could self-sustain. Once the first J-58 engine was started, the cart was repositioned to start the aircraft's other J-58 engine. Later start carts used Chevrolet big block V8 engines. Eventually, a quieter, pneumatic start system was developed for use at main operating bases. The V8 start carts remained at diversion landing sites not equipped with the pneumatic system. Brought to you by WikiVidi documentaries. Would you like to know more?